Students, you must have gone through my last few slides, especially the last one where we talked about plate tectonics, we talked about melt generations at different places, and we saw that there was also the possibility of sedimentation, metamorphic rocks. Our next point here is to study what is called time. Now, there are two ways to do time. One is to understand time in a relative sense, and the other one is to measure absolute time. So, I'm older than you, gives you no information as to what is your age. But if I tell you that you are 20 years old and I'm 20 years older, that would give you a numerical value. Then you say the rock is dated. So we know the dates at which the rocks formed. But from observing the rocks, we can find out relative times in which the rocks appeared. But for doing that, we need to understand a little bit about rocks. And then we will see, we will make it more and more complex, and we will try to understand how relative times of different events can be found out. But you don't get when it occurred. You only know that this occurred after that. So first we understand a little bit of rocks. As you know now, there are three types of rocks. One is called igneous rock. Igneous rocks. Now, igneous rocks are of two types. One is called plutonic rocks, and one is called volcanic rock. So you have plutonic igneous rocks and volcanic igneous rocks. Now, what are igneous rocks? Igneous rocks are formed when somehow, somewhere, you melt a rock. So when you melt a rock, what happens? The density of the melt, you are very conversant with iron melting. So pure iron solid to pure iron melt. But this does not happen in nature. You have what is called partial melting. So what happens is that when you melt a particular rock, the density of the melt is approximately 10% less than the original rock. So if there is a density of a rock which is 3 grams per centimeter cube, its melt would be 3 minus 0.9 into 3. No? Yeah. 3 minus 0.9 into 3. So it will be lower than the rock itself. So, when you partially melt a rock, whatever way it is, we will talk about that later. The tendency of the melt is to move up. Why? Because as you know, the density of the Earth or any planet increases towards the center. So, rocks above, as you go up to the surface, the density is lower. So what happens? When you melt a rock somewhere, the melt is less dense, so it generates a buoyant force trying to move up. So melts do not move down. But sometimes melt can spread along a zone of neutral buoyancy. So say, for example, you have a rock and you produce a melt, and the melt has a particular density, so it tends to rise and tip. And when it reaches the density of the surrounding rocks above, then it can't move up, because then there will be a gravitative inversion. Nature doesn't tolerate it. So what happens? If you keep producing melts, then the melts don't go above the zone of neutral buoyancy. So then it spreads laterally. Right? The other aspect to this is, when you melt a rock, the melt moves up, but when it moves up, it also moves into colder domains. So what happens? The melt dissipates heat to its surrounding, and by doing this, the melt also crystallizes. While the melt crystallizes, it releases heat to its environment. So essentially, the melt, as it rises up, it heats up the rock. The effects of that we will see. So the surrounding rock becomes metamorphosed. Right? Now, so we have rocks that we have the possibility of rocks being melted. Melts are lighter, they move up. As they move up, they become cold, releasing heat to the colder surrounding. So the colder surrounding gets affected, metamorphosed, and the melt starts to move up. But say, for example, when the melt is moving up, it gets access to a crack which goes up to the surface. So what happens? As you get that fissure out of that opening, the melt simply gushes out of the opening. And where does it go? It flows on the surface of the earth. Have you understood? So, when the melt moves up the crust through some fissures or through some cracks which are pre-existing, they move onto the surface of the earth and spread itself on the surface of the earth. These are called lava flows. And these rocks that are produced or formed on the surface of the earth, they are called volcanic rocks, because they come out on the surface, they are crystallized from the lavas that come in contact with the air, and they cool very rapidly. These volcanic rocks cool very rapidly because it comes up on the surface of the earth when it's 25 degrees centigrade, 1 atmospheres, and it cools dramatically. So they are cooled very, very suddenly. And these are volcanic rocks. Whereas, if those melts did not find a fissure or a crack to go up on the surface, then it crystallizes at a depth below the surface. These are called plutonic rocks. So plutonic rocks crystallize below the surface of the earth, and volcanic rocks crystallize from lavas that are emplaced on the surface of the earth. Now, as you can see by this process, since plutonic rocks cool below the surface of the earth, and it releases heat to the surroundings, so it crystallizes slowly. So because it crystallizes slowly, the minerals that are produced in the rock grow to large sizes. And finally, at the end of it, the melt completely crystallizes, and you have a completely crystalline rock. But if you look at the volcanic rock, then there is a difference. The volcanic rocks are formed because of its emplacement on the Earth's surface, and when you do that, it quickly cools, so growth of crystals in the very fast cooling magma is very, very little. So, volcanic rocks contains very small crystals, sometimes no crystals, sometimes microcrystals, but they produce very small crystal, and mostly is the melt that crystallizes into a non-crystalline material called glass. So volcanic rocks are essentially glassy in nature, and they are very, very fine-grained. Plutonic rocks, on the other hand, have no glass, and they are significantly coarser than volcanic rocks. I hope I made this point clear. So you have two broad classifications, plutonic rocks and volcanic rocks. Now, before we go into other rocks, there is an important point to make here, which may have escaped your thoughts. For an igneous rock to be formed below the surface, you got to have a rock before. And if you have to have a lava flow on something, there has to be a base for it. You can't crystallize a lava in the air. It doesn't crystallize. So ultimately, it falls onto the surface of the earth. So what you need is a pre-existing rock that existed prior to either the formation of a plutonic rock or the formation of a volcanic rock on the earth's surface. Now we go into something called sedimentary rocks. Now I don't go into the details of this because we will be talking about the details. Sedimentary rocks. Now we won't go into the details of classification, how it looks, what are the more critical factors. We won't go into that right now. It's just for an introduction. Sedimentary rocks are those that are formed on the surface of the earth. Right? They are formed on the surface of the earth, right on the surface. They don't fall below the surface of the earth. How are they formed? They are formed when water, ice, glaciers, or air transports material from one place to the other and deposits it. So say, for example, the glaciers from the hills, they come down, they have materials in them, the glacier melts, and the materials that they carry are deposited on the surface, on a base of a crust, or on a rock on which they deposit that material. So you have been to a river maybe, and you can see the river has a lot of sand. The sand wasn't produced there, the sand was brought from somewhere else and deposited. Say, for example, if you go to the ocean basins, for example, you will see a fairly thick layer of sediments. Have you understood? These sediments are called, if they are formed below the surface of water, they are called submarine sediments. They are called marine sediments. There are different names, but you must try and understand this, that sediments are deposited on the surface of the earth because of transportation by air, wind, and water, and deposited at a particular place. Right? Normally, for glacial and for sediments that are driven by air and water, they are deposited on a low, in a trough that they are deposited. But for aeolian sediments, that means air-driven sediments, air simply transports material from one part to the other. The sand dunes and the barkhans, this is how air travels. We'll go into some details of this. So we have a set of sedimentary rocks, materials, loose materials that are brought. Now what happens? These materials that are brought in by the glaciers, by the snow, the air, the ice, are loose. They are unconsolidated. They are not rocks. Like you go to the beach, sea beach for example, and you put your hands and take up the sand. And you take loose sands. They are not rocks. They are not bound by anything. They are very loose, so they are unconsolidated sediments. But as new and new sediments are deposited one over the other, that means the sediments at the bottom are the oldest. Sediments deposited on it are younger. Sediments deposited above it are still younger. So you have layers of sediments that are deposited on a particular base, a layer of sediments, older first, younger, and the youngest. So what happens is, it is deposited over time. But it would require a base on which the sediments are deposited. But they are loose sediments. Once you deposit sediments after sediments after sediments, they pile up. And what happens is, because of the piling up, there is a tremendous amount of pressure solutions. Tremendous amount of load generated on the lowermost bottom. What this does is, produces solutions, minerals are dissolved and reprecipitated. There are some solutions, for example, which percolate along the sediments. They are called cement and matrix, and they slowly consolidate the sediments. From unconsolidated sediments, to sedimentary rocks, they are no more loose. They are no more loose. So you have unconsolidated sediments brought in, deposited in a basin, thickening of the sediments, older one at the bottom, younger one at the top. This pressure creates a lot of solutions to migrate, binding up the loose materials, and you start producing a sedimentary rock from unconsolidated sediments. Now these sediments from different sources, etc., they can be identified. Not all can I tell you in this class, but those of you who are in geology will learn more. Those in geophysics, I think that would be the end of it. But I think it's common to say that sedimentary rocks deposit on a base. For the sediment to deposit, you've got to have a base. You've got to have a rock below. And then younger sediments are deposited. As younger sediments are deposited, solutions percolate and bind the loose material into hard rocks, and you produce harder rocks, sedimentary rocks from unconsolidated sediments. That's what you do. And this process more or less always occurs on the surface of the earth at the temperatures of 25 degrees centigrade and 1 atmosphere. Very different from the conditions which produce the igneous rocks, for example, which occur at thousands of degrees centigrades at very high temperature. Not all melts form at 1000 degrees. You can fall at even 700 degrees centigrade, but it forms at a higher temperature. The igneous rocks form at higher temperature. Below the Earth's surface, sedimentary rock gives a contrast. It forms at 25 degrees centigrade, 1 atmosphere. Now we come to the third type of rock, and these are called metamorphic rocks. These are called metamorphic rocks. Now, they are called metamorphic rocks because these rocks have undergone some sort of metamorphism. They have undergone some sort of metamorphism, which means that the pre-existing rocks had certain minerals, and those minerals were chemically and texturally modified because of some tectonic events that imposed itself on the rock. A rock itself doesn't do anything unless there are processes that operate on it. So what happens? Metamorphic rocks essentially are pre-existing rocks, but due to changes in pressure, remember pressure is the load, and the temperature, many of these pre-existing minerals undergo major mineralogical, even chemical changes in response to change in pressure, temperature, and fluid composition. So they produce, this is how metamorphic rocks is produced. For example, I was talking to you about plutonic igneous rocks. I told you, when plutonic igneous rocks, these melts are rising above, because they are going into a lower temperature zone, they are cooling themselves but releasing the heat of the surrounding rocks. You see, that's where metamorphism occurs. The surrounding rock undergoes metamorphism because now it has been subjected to a different set of temperature conditions. Even fluids are released into the rocks. So they undergo a change in the pressure, temperature, fluid composition. And these cause metamorphosis of a pre-existing rock. So these are called metamorphic rocks. Have you understood? Now, what happens? Metamorphic rocks generally they are related to deformation. This is an unknown term, but you can understand from plate tectonic processes that I talked to you before that plates are moving. You know, some place they converge, you have the convergent boundary. Some places they diverge, we are a divergent boundary. Some places them slide past each other. These are transform fault boundaries. So the Earth's crust, if you see the top part of the Earth, is constantly under stress. There is a stress field acting on the rocks. And so obviously a rock is strained. Have you understood? So rocks are strained. Very commonly they are under strain. They are strained. So say for example, if you say have a rock here, and say you have a pre-existing rock where minerals do not, for example, they are randomly oriented. It might so happen that if you apply pressure or stress onto the rock, what happens is, this is the zone of maximum shortening. And this is the zone of maximum stretching. I am taking here what is called pure shear deformation. Now what does this mean? Pure shear deformation. What does this mean? This means that this direction of shortening and the direction of stretching, which should be at 90 degrees, their orientation does not change in space. Have you understood? So, little more clearly, say you start with a square, this becomes a rectangle, and further stress would call it stretch to like that. But essentially, this orientation does not stretch. It can change in magnitude, but not orientation in space. So these are called irrotational shears. So the orientation of the stretching and the extension axis, they remain the same. Say they don't rotate. That is what is called a pure shear deformation. Irrotational shears. So when this happens, this rock shear undergoes strain. And when it undergoes strain, all these minerals which are anisotropic in shape, not circular, anisotropic, needle shaped, or something like that, not like a circle, for example, not like a sphere. So what happens? This rock then transforms. These minerals try to get aligned in particular orientation. Have you understood? Due to continuation of shortening here and stretching here. These minerals, instead of being randomly oriented, they become aligned. So sometimes it may so happen that you can have things like this. You might have a situation like this, where in these layers, minerals become finely oriented. Say, for example, they become oriented, and in between you can have also minerals which are, how will be the orientation? The maximum length will be parallel to the direction of stretching, and this will be the plane of flattening. Say, for example, have you understood? So what happens is that normally metamorphic rocks have some sort of a foliation. Folia means like that of a book, for example. Like a book. So you can have foliations. They have wonderful planar and linear features in them. So it's a very, very characteristic of them. The names like, for example, we will talk about them, schist, phyllite, gneiss are some common examples of metamorphic rocks where they have a mineral segregation learning, bending, and the minerals are aligned in domains parallel to it. It's all because of this type of deformation. But you can also think when the deformation is not of a pure shear, say for example, this is called, say for example, a simple shear deformation. So what happens in this? What happens in this? You have a deformation, say for example, just to give you an example, let's say this is a river, and say this is the top of the river. For you, I'm drawing a boat, right? Now what happens is, the velocity profile of a river, remember, the velocity profile of a river, if I take like this and draw the velocity profile, it has a structure like this, the velocity profile. That means this is the base over which the river flows. Now, the velocity here is smaller, the velocity here is larger, till here it is large, and then again the velocity decreases. This height is 2/3 the height of total river. The maximum speeds at which a river flows occurs at 2/3 the height from the base. Have you understood? Now, this is creating a little bit of a problem. Here, for example, at the base, it's zero velocity. It's called the velocity of no slip. No slip here. It's a theoretical term. There is always a slip. But it's called zone of no slip. And this increase and then the decrease, this decrease here is because of the resistance to air. Because of the resistance to air, you have a decrease in the velocity. So when you go to a river and you're swimming and you would like to go down, you should remember what AB told you. Don't go down too much. The speeds are faster. You better stick to the surface. So, but what is happening here, you see? This material is moving slower. This material is moving faster. This material is moving faster. So what is happening? It's like a pack of cards and you're shearing it like this. Have you understood? You're shearing it parallel to the surface. Have you understood? So what happens in a rock, if you take a rock now and do the same thing, your movement vector is now this way. Right? If you do that, your pure shear component and the simple shear component, this is the zone of stretching, and this is the zone of shortening. Have you understood? So what happens now is, you see again, the zone of stretching is at 90 degrees to the zone of stretching. This is called instantaneous axis that is generated. But as you move this, the two axes rotates. So this is involved, they're 90 degrees, but they're rotating around a central point, axis point. So what happens? These are called simple shears or rotational shears. So all deformations either involve pure shear or simple shear, or most have some percentage of pure shear and simple shear. But let's say if we take this simple shear component, this is the direction of shortening and this is the direction of stretching. So this random material, if they were there, now they align this way. Can you see that? Now they align this way. This is the angle along which the minerals get aligned. This angle was, in the pure shear component, this angle was 0 degrees. And this angle here is 45 degrees. So if you take the angle, it will also give you an idea of how much pure shear and how much simple shear component you had, qualitatively. But the important point is, your foliation here is at an angle to the walls of this shears or this deformation plane. So this also produces metamorphic rocks, but here the orientation of the plane of the foliation is not parallel to the shear zone wall as in pure shear, but it is at an angle. But nevertheless, it also produces metamorphic rocks. So now, we have talked a little bit about igneous rocks, we have talked a little bit about sedimentary rocks, and we have talked a little bit about metamorphic rocks, pre-existing rocks that are subjected to newer pressure, temperature, and composition. Pressure, temperature, and composition, they undergo mineral chemical changes. Why they undergo mineral chemical changes? Please wait, I will tell you. But they change the mineral temperature in response to pressure, temperature, and composition, and they normally have a well-developed foliation because deformation and metamorphism go hand in hand, and this imparts a particular fabric in the rock, which is called a foliation plane. We don't have a lab class this time. Otherwise, we would have shown you a lot of these rocks in a hand specimen and you would have been completely convinced. But this is how the three rocks are. But I will also like to tell you a little bit about deformation separately. All of you had mechanics, and I think your knowledge of mathematical mechanics is more than what I have. You may have understood, may have come across two terms. One is called brittle deformation, and the other one is called ductile deformation. We will go into these in this two types of deformations later on, but this is just to integrate you, to bring you at some point that, okay, we understand broadly, let's now go into deeper things. So it's called a brittle deformation and a ductile deformation. Very simply look. Brittle deformation, the rock breaks. A rock breaks. Say, for example, I have a rock and there is a plane, a plane developed. And the next stop, what happens is, you see, this point is now transferred to this point. There is no bending here. No bending at all. No bending. This is just breaking off. So say, for example, you broke your legs. So this is an example of brittle deformation, where rocks break. And take another example. This rock, you apply stress and it bends. That's where the rock is behaving in a ductile manner. Have you understood? So when a rock bends, it's a ductile behavior. There is residual strain in the rock. And this is what is brittle deformation, where the rock never behaves in a plastic or a ductile mode. There is only breakage across a plane. So we have both brittle and ductile deformation. For the sake of completing this, I will introduce you to two terms which will come in handy when we go on discussing this. Say you have a rock. Now, before I go into this, I would like to introduce you to two terms which all of you know, but we geologists use it very frequently. So, let us take a block diagram. Let's take a block diagram. You can see it in 3 dimensions. this is top, right? This is typically, everything in earth sciences is measured relative to north. Relative to north. This here, of course, you can understand, this is east, and this is west, and this is south. So, if I now translate this, and this surface now, I draw here, I will have north, obviously east, south and west. There is no top. This is called a plan view. This is called a plan view. So this is as if you are flying on a plane and you're seeing the surface right from the top. That's what it is. Look down on the floor, you see the plan. And these here are section views. How do I draw a section view? Say, for example, this plane. I draw this. How will I draw? This is top, of course. This is top. Right? And then this is east. So we now know if this is top and this is east, you're drawing this plane. If I said that this is west, you see, you have to look some other sections on which you have to do. You understand? Now this is called a section view. So we have plan view and we have section view. If you put the two together, you have a block diagram, a 3D view. So when you look at rocks, you always don't see both a plan and a section. Say you're going up a hill. When you're moving up on the hill along its flank, you're neither top, you're neither on a section, neither on a view or on the plan. You are going through an intermediate ground. It's something like no, my diagram is not so nice. So this is that we have sliced it. So we go up this. It's neither a plan nor a section. It's an inclined plane. So sometimes geologists always have to reconstruct a block diagram showing you the relationships on a 3D diagram. I'm telling you this because next diagrams when I do, I will be talking of whatever I will be talking, I have to do it on a 3-dimensional diagram. So I think I have another 5-6 minutes, maybe 7. So I will try and finish this section off before we slide on to the next. Let's we draw, say I am drawing a section view. Right. And I take and write this. Now you'll ask me, where is the top? Okay, here's the top. Where is the north? I say, I don't know the north. This is east. That means the north, you are looking north. Have you understood? You're looking north. So I take this section, for example. Let me first draw it and then I will tell you. I have drawn a section. This is the top view. And when I see this, maybe at the cliff of a hill, I see this. What do I see? This layer, you see here, this is a particular layer. And the same layer is displaced here. So this part has moved down. Have you understood? This part has moved down. Now, if you look at this part, it's different. With respect to this, this has moved up. Although the angle of both has remained the same. This, and what are these lines? Obviously, the answer is they're faults. These are faults. So, this is a fault and this is a fault, but there is a difference. They're inclined faults, but in one case, this part, now I'm saying this part, I will explain it to you, this part. This part has gone down relative to this, and here, this part has gone up relative to this. Now I'm saying this part, what is this part? Now there are two terms. One is called the footwall, and the other one is called a hanging wall. I will explain. These are very old terms. These were not used by geologists. Geologists only took it up. These two terms were very much used by miners. So what happens? Say, for example, I am drawing now. Say this is a place you can understand, it's a section view. It's a section view. This is the ground, there is a tree and there is a shaft from which there are other shafts. For example, here another shaft has been drawn. Let's say this is a mineralized zone which miners were mining to extract the minerals. Now when they are doing so, you look, if they have to dig, then their head will be here and their legs will be here. You see that? So the place where this is called the footwall. And the place which is above their head, hanging above their head, these are called hanging walls. So you have a footwall and a hanging wall, given by miners long ago. Now if you transfer this information here, this is the hanging wall. Have you understood it? If there was a mining going on here, the miner would have stood with his head on this side. You can't mine with your head down on the floor. You have to stand up and mine. So this is called the hanging wall. And therefore this is the footwall. Have you understood? Here, this is the footwall. This is the hanging wall. The one on the head. So, this is footwall. This is hanging wall. So, if this is hanging wall, this is footwall. Now you can say, how is this, sir? You are saying this is footwall, then this is hanging wall. How did the footwall become an hanging wall? No. It's not like that. It is like, with reference to a fault, in that zone, you have a footwall and a hanging wall. It's not that you have a footwall right from here to here. No, it doesn't happen that way. It's always relative to the neighboring areas of a fault. So, faults are indicative of brittle deformation, bent rocks are examples of ductile deformation. Brittle deformation involves two main types of faults, which you should know because we will be using it. One is called a footwall, one is called a hanging wall. And then when the footwall moves down, when the hanging wall moves down relative to the footwall, you call it a normal fault. This is called a normal fault. In normal fault, the hanging wall moves down relative to the footwall. And this one here is called a reverse fault. What is it? Where the hanging wall moves up relative to the footwall. Both are faults, but they have a different sense of movement on the fault line. So you have a normal fault where the hanging wall moves down relative to the footwall, and you have a reverse fault in which the hanging wall moves up relative to the footwall. We will expand on this. Thank you.